All right, so this question is about determining polarity. Okay, and the question is a methane molecule, for example, polar or nonpolar? So let's look at that. Methane. And methane, the meth prefix means there's only one carbon. The ane suffix means there's only single bonds between carbons. Well, if you only got one carbon, you can't have any double or triple bonds. There aren't any bonds between carbons if you only got one. So methane is CH4. So what we need to do is to figure out the three-dimensional structure of it first. Okay? So we've got a carbon, and carbons have how many valence electrons? 4. 1, 2, 3, 4. And hydrogens have how many valence electrons? 1. And we've got 4 hydrogens. And the only way that this one can go together is if you share these electrons to complete the valence level of both the hydrogens, or all the hydrogens, and the carbon. Okay, so we started out with the black markings there were the electron dot formulas, drawing the circles to show how they're sharing. That's called the sharing arrangement. Now we're going to write a Lewis dot formula, not a Lewis formula, but a Lewis dot formula. I'm not sure if technically Professor Lewis or Dr. Lewis intended these to be called different names, but I like to differentiate this between a Lewis formula. So what we're going to look at is to see how many sets of electrons we have around the central atom. And the sets of electrons we have around the central atom are either lone pairs or all the electrons share between two atoms. And so we've got a set here. All the electrons shared between these two atoms is 2. All the electrons shared here is 2. So there's 4 sets of electrons around this atom of interest. So in high school chemistry, we mostly deal with really simple molecules. We could say the central molecule, but when you get to college chemistry or AP chemistry, when you have to do more organic kind of stuff, you need to look at larger structures, like those organic structures we learned to name and write structures for just a moment ago. So for now, we're sticking with the central molecule, or central atom is the most important one we're interested in here. And since we have 4 sets of electrons, we have to arrange those 4 sets as far apart in space as we can get them around this atom of interest. And the angle for spreading those out is 109.5 degrees. And it forms what's called a tetrahedral. Okay? I'm sorry. Yeah, tetrahedral. Not to be confused with a tetrahedron. All right, so a tetrahedral then you have a set of electrons going in this direction. The next set goes at 109.5 degrees. The next set needs to go at 109.5 degrees. But to get them all in there, 4 sets at 109.5 degrees, I've got to have one angle coming out away from the paper. And the way we show that is a triangle. Okay? How many of you take art? Anybody taken art before? Okay, you know what perspective is. We're basically doing a really modified, simple, because, chemists are not really supposed to be really good artists necessarily. So this is a modified form of perspective, okay? And so we're going to draw this one goes back behind everything. And we have electron dots like that. And we call this the electron pair shape. Or that's what I call it anyway. Okay? Now, this shape is a tetrahedral. So this is like it has 2 names. The first name is tetrahedral, and the last name has more than one name. Okay? Electron pair shape. Okay? 3 names in the last name. Okay? Now, the next step we're going to take is to take any sets of electrons in this drawing that are shared in this drawing. We're going to replace those sets with the atom they are shared with. So we're going to put this here. We're going to put a hydrogen on here. And it turns out all these, you can see, are shared. So we're going to put hydrogens on all these arms or legs, whatever you want to call them. All right? And so now that there are no more pairs of electrons left, we're done. This is now the molecular shape, and since it's the same shape as this is a tetrahedral molecular shape. Okay? That's the first thing. We've got to find the 3-dimensional shape. The next thing is, to find out if it's polar or not, we have to have 2 conditions for a molecule to be polar. And if it's not polar, then it's nonpolar. Okay? And the 2 conditions are, you have to have an uneven arrangement of bonds, and you have to have both, and you have to have polar bonds. Okay? Now, if you do the electronegativity difference for this, you'll find out that it's right at that boundary of being polar or nonpolar. Okay, but it doesn't really matter because it's evenly arranged. If you don't meet both conditions, you can't have a polar molecule or some polar portion of a molecule. And you'll find out about that when you do organic chemistry in college, or especially biochemistry. That's when you really get into all that. You do it some in biology too, because this is why it is that the DNA molecule stays together the way it stays together. Okay, the polarity is why your heme and your hemoglobin and your bloodstream works. Okay, because of this polar or polarity. All right. So we don't have to do any calculations. We don't have to do any other stress over this. This is evenly arranged. We have a nonpolar molecule. Now here's a little trick. That's a trick. It's not always true, but almost always true in high school chemistry. That if you don't have any lone pairs, you're not going to have a polar molecule. Okay? Not always true, but most of the time, because that's the only way you can get an uneven arrangement, is to have some lone pair somewhere. Got it?
So it could be trigonal planar.
Mm-hmm.
That could be one that.
Yeah. Well, you can actually have a polar molecule that's trigonal planar that doesn't have lone pairs on the central atom. Okay, but that has to do with an uneven arrangement of the polarity. Okay, let me show you one, for example. Let's do formaldehyde. Okay, so formaldehyde is CHO. Okay, all right, and we hear a lot of this time of year. I'm sorry, CH2O. Yeah, CH2O. Okay, what is it? Formaldehyde.
Why do we hear a lot about it?
I know, sad chemistry joke, but anyway. So carbons have 4 electrons, oxygens have 6, hydrogens have 1. We want to have each of these atoms to have a full valence level of electrons. So we're going to share here, and the only way to get carbon to have 8 valence electrons, this is what it wants. Hydrogens want 2, but most things want 8. Both the carbon and the oxygen need to share 2 electrons to get to this full valence level. Okay? So then we're going to find an arrangement here using Lewis dots. So there's a double bond then between the carbon and the oxygen. Okay? And there are single bonds going to these hydrogens. Single bonds mean I'm sharing 2 electrons between the 2 atoms. Double bonds mean I'm sharing 4. So there's got to be a sigma and a pi bond here. We don't get into that right now, but that's what it is. And now what we want to do is to find an arrangement of these sets of electrons and get them as far apart as we can get them. So we've got a set here and a set here, and this set of 4 makes up a set. Okay, all the electrons shared between 2 atoms make up a set. Lone pairs can be a set, and all the electrons shared between 2 atoms make up a set. So we've got 3 sets here, and the arrangement that gets those as far apart as we can get them is trigonal planar. Okay, so I'll put 2 electrons here, 2 here, and 4 on this one. Okay, and then we're going to replace those with the atoms if they are shared. If they're not shared, we'll leave the lone pair on there. We don't have that in this case, but if that were the case, we would. So we'll put a hydrogen here, and a hydrogen here, and then an oxygen here. All right? So now we've got to figure out about the polarity. So let's look at our periodic table and kind of do some estimations here about polarity. You should know, just because we've worked with it enough, that the difference in polarity between, our electronegativity between carbon and hydrogen is about 0.5. Okay? Now if you wanted to go back and look at the other part, the homework references I gave you, and just verify that to help you remember these things, there is a periodic table on the homework references, not one you can use on the test, but the homework references, and you can actually see the actual amount of electronegativity here. Okay? And it's ever so slightly less than 5, but pretty close to 5, okay? Which is right at the boundary line, for us anyway, for determining whether we have a polar bond. Okay, now some textbooks say the difference in electronegativity ought to be 0.3 instead of 0.5. There's really a lot more to polarity that we don't get into in high school chemistry. that we can't get into just because we're trying to introduce you and keep it simple right now. So just remember, when you go to college and you're learning all this stuff all over again, I told you that there's a lot more to polarity, okay? All right. So we know that this is on the boundary line of being polar. Well, if we know that also that because of where carbon and oxygen are located, that the oxygen, it has about a difference in electronegativity of about 1, which is clearly in the polar range. The polar range is between 0.5 and 1.5 for us, okay? If you wanted to verify that, you can go over here and look at it, and it's slightly more than 1, okay? But it doesn't matter. Between 0.5 and 1.5, that's a polar range. So this is clearly polar, and it's clearly polar going in that direction. Okay, does that make sense? This is far more electronegative than that one is. Got it? And this one's almost, I mean, it's like it's almost there. It's just barely not making it, okay? So because, though, this barely not making it sort of polarity is going in this direction, and this is going in this direction, it's like a river, okay? You've got two tributaries flowing together, and this is all going downhill this way. Overall, the polarity of this molecule goes in this direction, because this is clearly polar, and this doesn't fight against it. It's not going in the opposite direction. That's a polar molecule, and there are no lone pairs affecting it.
And that's how you draw it. The ones that aren't quite polar, you point in. And the
No, this is just, carbon is more electronegative than hydrogen. That's why I did it. But I made it in red because it's right on that boundary line. I'm just showing that it's not boundary line, but headed in that direction, okay? Because even if it's boundary line and headed in that direction, it would pull against this polarity, and it, at least for the high school level, be a little bit too complex for you guys to be expected to figure out. Some of you might be able to figure out, some not, but we're not. I won't give you one like that. Okay. This one I think you can figure out. Okay. Because overall the polarity goes in that direction. Got it? All right. Any other questions about how to figure out polarity of a molecule?